mathematics. How much gold can you hold in an elephant's ear? When it's noon on the moon, then what time is it here? If you could count for a year, would you get to infinity or somewhere in that vicinity? When you choose how much postage to use, when you know what's the chance it will snow, when you bet and you end up in debt. Oh, try as you may, you just can't get away from mathematics.
Hi calculus class, welcome back. It's been a couple of days since I posted a video for you, as we only meet a couple of times a week. I didn't get any questions on the velocity and acceleration questions that you were to do from Monday. And so today we're going to move on. We're going to start into our second application of derivatives, which is optimization. Optimization really means maximizing or minimizing quantities to create efficiencies in things. And so I've got a graph behind me here on the wall. We're going to get right into it. Why not? Why waste time, right? Get right into it here. We've got our graph here. We can see on the graph that we have this particular domain. It goes from beginning to end, and there's closed dots there that mean that that is the end of our function. And within our function, we've got a couple of high points and we've got a few low points as well. So we have a number of what we call local maximums, local minimums. All right, so anytime we get to a high point, that's a local maximum, and the low points are local minimums. And within those local max and mins, we also have what are called absolute max and mins. An absolute max and min would be at the absolute highest point that this function gets to. There we have an absolute max, and within this domain we have a absolute minimum as well, the lowest point that this function would go. So those are maximums and minimums. Now how do we find those maximums? Well, to find those maximums we have to realize something about what are called critical numbers. Critical numbers are numbers in the domain of a function that either make the derivative f primed of c equal to 0 or make it not exist. So critical numbers are numbers that make the derivative of the function either equal to 0 or make the derivative undefined. And so if we can find those numbers, those critical numbers, that's where the maximums and minimums will occur, because if the derivative equals to 0, we know that that means we have a horizontal tangent line, right? Remember, derivative is slope, and if the derivative equals to 0, that means the slope is 0, which means we have a horizontal line, and that is where our maximum will occur, or minimum, okay? Here as well. All right, so when we're doing max and min problems, we're going to be presented with a situation, a real-world situation. And we're going to be looking at trying to maximize or minimize a quantity. And so we're going to have to take the situation, the question. We may need to draw a diagram to picture it a little bit. We're going to introduce some variables into it. And we're going to look at what is the quantity that we're trying to maximize or minimize, and we're going to find a formula for that quantity that uses the variables that we've introduced in our diagram. And then we're going to take the derivative. And we're going to make the derivative equal to 0. And then that will allow us to find the critical numbers, and which would then allow us to find the maximum or minimums. Now, a lot of times in those real-world problems, it's not actually the max or min we want the critical number. The critical number tells us what should be happening in order to get a maximum or minimum, and that's often what we want rather than the actual max or min. I've got an example on the board next to me, so we're going to walk over there and we're going to look at an example. So here we've got an example on the board. I've already sort of drawn the diagram and written it out, but here it is. It says, a long rectangular sheet of metal, 12 inches wide, is to be made into a rain gutter by turning up two sides so that they are perpendicular to the sheet. How many inches should be turned up to give the gutter its greatest capacity? And so what we're doing is we're taking a long rectangular thing, we're folding up two sides, creating a gutter that looks something like this. All right, and we want to maximize the capacity of the gutter, which would mean maximizing this cross-sectional rectangle that would be here. And so I've tried to draw that. You get to see a little bit of my artistic skills here. Here's our long piece of metal that is 12 inches wide. I'm going to take it, I'm going to turn up two sides so that they're perpendicular. I'm going to call those two sides that I turned up X. And that means that the width of this gutter now is 12 minus those two X's. And in order to give it the maximum capacity, the greatest capacity, we want to maximize the area, the cross-sectional area of the gutter, which I shaded in red. So, area is the quantity that we want to optimize. We want to maximize the area, so we need a formula for area. Good thing we know that area is length times width, and in this case, area equals X times 12 minus 2X. We're going to simplify that, multiply the X through, giving us 12X minus 2X squared. All right, so here's our formula now for area of the cross section of the gutter. And it's that we want to maximize. So again, now to find the max and min, we want to find the critical number. We're going to recognize that the max and min will occur at the critical numbers. So to find the critical numbers, we need the derivative, because we're going to remember that critical numbers are numbers that make the derivative equal to 0. So let's find the derivative. I'm going to come over here, we'll rewrite it over here. So now a prime, the derivative, is going to equal 12 minus 4x. There's our derivative. Let's make that derivative equal to 0. And let's solve for x. There we have it. We get x equals to 3. So x equals to 3 is the critical number. It's not the maximum area. It's the critical number. It's the number where the maximum would occur. But it's x that we want to find, right? The question is asking us how many inches should be turned up. Well, it was x that we turned up, okay? When x is 3, that will give us a maximum area, which will be the maximum capacity. So in answer to the question, how many inches should be turned up? 3 inches on each side should be turned up to maximize the capacity of this gutter. Let's go look at another example on the board to my right, and we'll do another one. Here's example number 2. On this board now, what we've got is we've got a problem that involves a box. We're going to make a box. So it says that an open box with a rectangular base is to be constructed from a rectangular piece of cardboard 16 inches wide, 21 inches long, by cutting a square from each side, from each corner, and bending up the sides. Find the size of corner square that will produce the box with the largest volume. So what we've got is we've got a piece of cardboard, 16 by 21, and we're going to cut corners out. And then we're going to take this and we're going to fold along these blue dotted lines. We're going to fold them up, and that's going to create us a box that has a height of x, a base of 16 minus 2x, right? We took x and x out, and 21 minus 2x for the length, again cutting x and x out of the corners. So this is our box, this is our setup. We want to produce the box with the largest volume. So we want to maximize volume. So that means that we need a formula for volume of a box. Again, we know that. The formula for a volume of a box is length times width times height. Again, you all know that. And we're going to make this x times 16 minus 2x times 21 minus 2x. So there's our formula for volume, and we want to now, in the end, what we want to do here now is, when we get to the end, we want to find the derivative, we want to make the derivative equal to 0 of this function. Now, I don't want to do it this way, I don't want you to do it this way. What I want you to do first is I want you to take this, I want you to multiply it out, okay? So that would take a little bit of work to multiply this out. There will be a common factor of 2 that I want you to then factor that out. And so what you should end up with, and I'm not going to do it for you, I'm just going to write down the final answer here. What you should get in the end is you should get that the volume equals 2 times 2x cubed minus 37x squared plus 168x. Okay, so you're going to multiply this out, you're going to factor out the common factor of 2, and that's going to leave you with this function for volume. And we want to do this because it's far easier now to take the derivative of this function than it is of this multiplication of 3 factors. So now I want to take the derivative of this. And again, you can see this as a product rule. It's 2 times this. So when we take the derivative, it's going to be 2 times the derivative of this piece in the brackets plus the derivative of the derivative of 2, which is 0, times this. And so we don't need that second part. We're just going to do 2 times the derivative of this second piece to find our derivative. So here we go. We're going to go v prime. It's going to equal 2 times 6x squared minus 74x plus 168. All right, so there's our derivative. We now want to factor that one more time. So there's a common factor of 2 here again. So let's factor out the common factor of 2 again. That's going to leave us with 4 times 3x squared minus 37x plus 84. All right, we're going to make this equal to 0. And we now have to either factor it, and it does factor, but if you don't want to factor something like this, you can certainly use the quadratic formula. I will factor it for you. It does factor into 3x minus 28 times x minus 3. All right, and again, we're looking for the critical numbers here. The critical numbers are the values of x that make this equal to 0. So x would then equal to either 28 over 3 or 3. Now, those both aren't correct answers. Remember previously, a couple minutes ago, we talked about the domain of the question. Okay, this question has a domain. If we look at this box, okay, there's a domain for x. We can't just make x anything we want, right? X has to be between 0 and 8. It can't be 0. If we don't cut a corner out, we don't get a box. And if x is 8, then this width becomes 16 minus 16, which gives us the width of 0. So the amount that we're cutting out has to be between 0 and 8. It can't be 0, can't be 8. It's got to be between 0 and 8. If we look at these numbers, 28 over 3, well, that's greater than 8, right? If we were to simplify that. Or if we were to change that to an improper fraction, or sorry, a mixed fraction is an improper fraction, then we get a number that's greater than 8, and this is not in our domain. So this cannot be the critical number for this question, and 3 is. And so when x equals to 3, we will get the box with the largest possible volume. And so the question asks us to find the size of the corner square. Well, the size of the corner square was x by x, so our answer to this question is 3 by 3. A 3 by 3 square should be cut out of the corners to produce the largest possible volume. I want to give you one more example. I'm going to go over to the other board again and do it there. And for our last example, we want to look at minimizing a cost. We want to create a cylindrical container, a soup can, if you will, where we want to minimize the amount of material, the amount of cost that will cost to make this thing. So the question would be a circular cylindrical container, open at the top, is to have a capacity of 24 pi inches cubed. So that's a volume that it's giving us. The cost of the material for the bottom part is 15 cents a square inch, and that of the material for the sides is 5 cents per square inch. So we got the bottom material, we've got the side material, each have their costs. We want to find the dimensions that will minimize the cost of the material. So I've drawn a little diagram, simple, just a little cylindrical container. It's got a height and it's got a radius. All right, so to minimize the cost, we need a formula for cost. Well, the cost is going to be 15 cents times the area of the base, whatever that is, plus 5 cents times the area of the side. Plugging in some formulas here, area of a circle on the base is pi r squared. Area of the side, it's going to be the circumference of the circle, because that's going to give us the side length, and then times the height of the cylinder. All right, so circumference times height will give us it. And again, if you imagine rolling a piece of, imagine rolling something up, okay? We've got our bottom circular base, and when I pull this apart, it becomes a rectangle where the circumference of the circle is this, and then the height is this side. And so that's where we're getting that formula from. I've factored out a 5 pi. If we see here, we've got a 15 pi and a 10 pi. It's a common factor of 5 pi, so I pulled that out front as just a constant. It's going to make the derivative equal easier to take, leaving us with 3r squared plus 2rh as our formula for the cost of the material. Now there's a slight problem with this formula. It has too many variables. We've got c, we've got r, and we've got h. That's too many variables to take the derivative. We need to find a way to eliminate a variable. And to do that, we're going to go back to the question. The question gave us a piece of information we have not used yet. There it is. It tells us that the volume is 24 pi inches cubed. The volume of a cylinder, the formula for that is pi r squared h. And again, the area of the base times the height is the volume. And with this, we can plug in our 24 pi for the volume. And here we have a choice. We can either solve for h or we can solve for r. The point being that we're going to solve for one of those variables, and then we're going to make a substitution into here, which will allow us to get rid of one of the variables in our cost formula. It's much easier to solve for h. So we're going to divide both sides by pi r squared, and that's going to give us the formula for our equation that's equal to 24 over r squared. Pi's, of course, cancel out, and we're left with this. Okay, we're going to now take that, we're going to put it in for h in our cost formula. So cost will now become 5 pi times 3r squared plus 2r times 24 over r squared. We are going to simplify that a little bit, and I'm just going to do it by erasing and adding. We have an r over an r squared, and so this r can disappear, and the squared can disappear, leaving us with 2 times 24, which is 48 over r. All right. Okay, there's our formula. We now want to do the same thing we've done on all the other questions. We want to take the derivative of this. We want to make that derivative equal to 0, and that will give us our critical number. Now, it will tell us what r is, and at that value of r is where we will find our max and min. In this case, it's a minimum. And we'll be able to answer the question of what dimensions will this be. So let's quickly do that. We'll go C primed. And again, we're using a product rule here. We have 5 pi, which is just a number, times this. And so we'll do 5 pi times the derivative of this, plus 0 times the other piece. And so the second half of the product rule will just be 0. So we don't need to write that out. If we take the derivative, we're going to get 5 pi times 6r minus 48 over r squared. Okay, so again, if we're looking here at this r, we're going to move into the numerator. It becomes r to the -1. Multiply the -1 out front, reduce the exponent by 1, drop it back into the denominator, and we are left with this. All right, now we want to make this equal to 0. Okay. To make this 0, we just need to make this piece in the brackets equal to 0, so we can ignore the 5 pi, or if we want to, we can divide both sides by 5 pi, and then it won't be there. To make this equal to 0, we're going to look at just that piece in the brackets, and I'm going to get a common denominator. So I'm going to take this r squared, make a common denominator. That's going to give me 6r cubed minus 48 over r squared. I'm going to factor the numerator. which will leave me with this. Now, the critical numbers, again, are values of r in this case, that will make this equal to 0. And so if we have this, we can see that the critical numbers are at 0, because 0 makes the derivative undefined, does not exist, or r will equal to 2. And again, r can't equal to 0 because it's not in the domain of our function. In order to have a container, it has to have an r that's greater than 0. So we're going to ignore the 0, but here r equals to 2. And so the radius of our cylinder should be 2, and to find the height, we're going to come back over here to our height formula. We're going to put 2 in for r, and we're going to get 24 divided by 4, and the height should be 6. So the dimensions of our container should be a cylinder with a radius of 2 and a height of 6 inches. Hope that makes sense to you. You can again watch this over and over again. You can do the math yourself. You can figure this out. Your assignment is going to be a few questions, both out of your textbook and in a handout. You'll find those instructions on Connect. This is our last lesson of the week, so have fun on spring break, enjoy the break, and we come back after spring break. We'll review all of this, make sure that it's going well, and then we'll move on to our final application, which is related rates. As always, if you have any questions, please let me know. Email me your questions, and I can get out answers to you over spring break if need be. And yeah, we'll go from there. I hope you are enjoying your time at home. Our verse of the day today comes from Psalm 94. Verses 18 and 19. I know many of you heard this in the physics lesson already today, but it's worth repeating. And I'll just read the verse to you here. And it says, and this is again David speaking to the Lord, he says, "When I said, my foot is slipping, your love, O Lord, supported me. When anxiety was great within me, your consolation brought joy to my soul." So may you have joy in your soul. Enjoy spring break. We'll see you after the break. Yeah, we'll keep going with this. Have a great day. Bye.